Welcome to Fundamentals of Hypothesis Testing Methodology. This is the first lesson of 3 for this unit. In this lesson, I'll provide an introduction to hypothesis testing, discuss how to choose a test and then interpret its results, and provide a short summary of the lesson. Let's start with hypothesis testing, and what is it? Hopefully, the information on this slide about research questions and hypotheses is familiar to you already, but it never hurts to review. With research questions, we are formulating what we want to know. These should be able to be written as questions. For example, what is the average height of students at the African Institute for Professional Development? With our hypotheses, we are making a prediction about something. This prediction is often the relationship between some variables of interest, or the effect of some variable or action on another variable. Hypotheses should be able to be written as declarative statements. For example, the average height of students at the AIPD is 1.7 meters. The type of hypotheses we want to test and the type of data we have determine the type of test we will use. If you were to search for steps in conducting a hypothesis test, you would find lists of steps ranging from 3 to 7 steps. Some of the steps wouldn't even follow the same order as this list here. But this is the basic process that we'll follow in this lesson. The reason for the differing number of steps is that you can formulate your research question, and thus your hypotheses, to ask a number of questions about your data, including about the shape of your distribution. For instance, you could ask if the daily number of homicides in the United Kingdom follows a Poisson distribution. You can use a goodness of fit test, such as the chi-squared goodness of fit test, in order to test that hypothesis. Moreover, the number of individual steps really depends on how specific an author is in describing the steps. Before we can get started with hypothesis testing, we first have to understand the nature of the statistical problem that we want to solve. When we have only one sample, we can't compare the statistics of multiple samples. Rather, we typically ask if the statistic from the sample that we do have is higher or lower than some other value. For example, is the average height of students from the AIPD higher or lower than 1.7 meters? We call this a one-sample hypothesis, or one-sample problem. When we have 2 or more samples, we can compare statistics from the different samples. We call this a two-sample hypothesis, or problem. In the case of 2 independent samples, the members of the 2 samples are different people, such as a test and a control group. For example, are the students of AIPD taller or shorter than the general population of Rwanda on average? In the case of 2 dependent samples, the members of the 2 samples are the same people. The samples may have been taken pre- and post-experiment, or they may have been taken longitudinally. For example, are students of the 2020 AIPD graduating class taller or shorter than those of the 2021 graduating class? When conducting hypothesis testing, you will always have at least 2 hypotheses, the null hypothesis and the alternative hypothesis. The observed values, the data that we are working with, will always include some variation due to chance. However, we can ask if the variation in the observed values is due to chance alone, or if there is a real relationship or effect that is also observed. The way we formulate this is the observed statistic of our sample is equal to some value. For example, the average height of AIPD students is 1.7 meters. The alternative hypothesis is formulated as the observed statistic of our sample data is not equal to some value. In this example, we could say the average height of AIPD students is not 1.7 meters. This is also the stage at which you'll identify the relevant statistic. What values are you trying to compare? The number of coin flips? Mean heights or weights? What is the most relevant statistic for your research question? It is important to remember that when we test our hypotheses, we are not proving that our alternative hypothesis is true. Instead, we are saying we believe we can reject the null hypothesis in favor of our alternative hypothesis. Therefore, we are not conducting equivalence tests in which we prove that a parameter is equal to a predefined value, or that two parameters are equal. While we won't be covering equivalence tests in this course, you can investigate them more on your own. So next, decide if you're interested in a one- or two-sided alternative hypothesis. Both one- and two-sample problems can be tested with one- or two-sided hypotheses, although it is more common to test one sample problem with a one-sided hypothesis. With a one-sided hypothesis, we test to see if one sample statistic is less than some value, or the same statistic from another sample. We can also test if the statistic is greater than the value or other sample statistic. For example, a null hypothesis could be that AIPD students have an average height less than or equal to 1.7 meters, or that AIPD students have the same average height of the general population of Rwanda. The alternative hypothesis in the first case would be that AIPD students are taller than 1.7 meters on average. An alternative hypothesis in the second case could be that AIPD students have an average height less than the general population of Rwanda. With a two-sided hypothesis, we test if one sample is not equal to the other. Our null hypothesis is that the two samples are from the same population, so the observed statistic will be the same. Our alternative hypothesis is that the two samples are from different populations, so they will have different observed statistics. Now let's consider how to choose the appropriate test for your hypotheses. How do you choose a test? A choice of a hypothesis test is dependent on three characteristics of, or assumptions about your data. The first is that your data is independent. The chi-squared and other independence tests are a good way to test the independence of your observations. If your hypothesis is focused solely on whether your observations are independent, then you can stop here. If your data is not independent, then you can use a paired t-test for dependent data. The second assumption is that your data follows a normal distribution. If you need to test the shape of your distribution, i.e., whether or not you have a normal distribution and your data is parametric, then you can use the chi-squared and other goodness of fit tests. If you have non-parametric data, then you'll need to consider the Wilcoxon-Mann-Whitney test. The third assumption is that your variance is homogeneous or equal. If it is, you can use a Gauss test if the variance is known, or a t-test if it is unknown. If you don't know if your variance is equal, then you can use a Welsh test. As you can see, there are quite a few possible tests that you may want or need to use for testing your hypotheses. We will not cover most of them in detail, but in the next 2 lectures, I'll discuss Z and t-tests and ANOVA. I recommend that you read about each of them. I've noted some important characteristics of each test. Choosing the appropriate test will depend on the characteristics of your data. Now that we've looked at how to choose a test, let's discuss how to interpret the results and draw conclusions. Although we're not quite ready to make a decision about the results of our hypothesis test, we need to think ahead to ensure that we don't draw the wrong conclusion. One way to think about how to evaluate our findings is using a confusion matrix, like the one on this slide. A confusion matrix helps visualize possible conclusions. Here, there are 2 types of correct conclusions: true negatives and true positives, and 2 types of incorrect conclusions: false negatives and false positives. We call the incorrect conclusions type 1 and type 2 errors. For example, let's have as our null hypothesis the claim that none of these images are of hot dogs. For the images in the first row, we see that our null hypothesis is true, meaning neither picture is of a hot dog. Looking at the first image of the pizza, if we accept the null hypothesis because it is true and conclude that a pizza is not a hot dog, we would be correct. However, if we look at the picture of the dog in the hot dog costume and reject the null, thereby concluding that the dog is a hot dog, we would be incorrect. This false positive is a type 1 error. The probability of making a type 1 error is equal to the probability of accepting the alternative hypothesis instead of the correct null hypothesis, and is given by alpha. With the images in the second row, we see that our null hypothesis is false, meaning that both pictures are of hot dogs. So if we look at the picture of the chili dog and accept the null, thereby concluding that the chili dog is not actually a hot dog, we would be incorrect. This false negative is a type 2 error. However, if we see the picture of the classic hot dog and reject the false null hypothesis, we would correctly conclude that we have a hot dog. The probability of making a type 2 error is equal to the probability of accepting the false null hypothesis instead of the alternative hypothesis, and is given by beta. Now that we know about the types of errors we can make, how do we make sure that we don't make any errors when we make our decision about the null hypothesis? We conduct a significance test. A significance test allows us to determine how likely it is that the test statistic is not due to random variation. If it is very likely that our test statistic differs from the null hypothesis for non-random reasons, meaning the sample is truly different, then we can reject the null hypothesis We call this likelihood, or probability, the p-value. Let's consider the XKCD cartoon here. Aaron says that he is dating a number of people, and that while he might see one person more than the other, it is due to random chance. So Marcia may be studying for exams this week, so he spends more time with Felicia and Tanya. But over time, he claims that he spends the same amount of time with all the women. That is his null hypothesis, that there is no true difference in the amount of time he spends with any single woman. However, Tanya says she's an outlier. Her alternative hypothesis is that Aaron spends much more time with her than he does with Marcia or Felicia. If she can calculate a p-value that falls below a pre-specified alpha level, Aaron should reject his null hypothesis and call himself Tanya's boyfriend. How does this relate back to our type 1 and type 2 errors? Our significance level, alpha, is essentially an indicator of how willing we are to make a type 1 error. Remember that type 1 errors mean we reject the null hypothesis even when it's true. For Aaron, this could mean breaking up with Felicia and Marcia, even though he doesn't actually spend more time with Tanya. But it could also mean incorrectly rejecting a null hypothesis of innocence in a criminal trial and convicting an innocent person. Since type 1 errors tend to be the more severe errors, we try to minimize our alpha and maximize our confidence that we will calculate a statistic that will not allow us to falsely reject the null hypothesis. Common values for alpha are 0.05 and 0.01. Since we're looking at values distributed around the mean, we subtract alpha from 1 to calculate our confidence level. The power of the test is the probability of not making a type 2 error and thus correctly rejecting the null. In order to minimize beta, we need to account for it in our sample size calculations, which was covered in Lecture 6. So now let's pull it all together. We assume that observed values will have a standard normal deviation, meaning some extreme values are possible even with random variation. In order to know if our observed value is really different from that of our null hypothesis, we calculate the z-score. The z-score is essentially the number of standard deviations between the observed statistic and the null value. Z-scores provide a standardized value which captures a certain percentage of the values of a population. The z-score is equal to the number of standard deviations away from the mean that corresponds to our desired confidence level. The p-value is the probability of our observed z-score being greater or less than the z-score under the null hypothesis. If our alternative hypothesis states the observed z-score will be less than the null z-score, then we look at the right-hand side of the distribution curve. If we think it will be greater than the null z-score, we look at the left-hand side. If we have a significance, or alpha, level of 0.05, we would have a confidence level of 0.95, or 95%. This is about 1.651 deviations from the mean, so that is the z-score we would use. In a two-sided test, if we have an alpha of 0.05, we would have a confidence level of 0.95 or 95%. Two standard deviations from the mean includes slightly more than 95% of the values, so we use a z-score of 1.96 to capture exactly 95%. There are a number of online reference tables and calculators, as well as statistical programs that will help you determine your observed z-scores and p-values. Once you calculate the p-value, compare it to alpha. If it is below alpha, then we reject the null hypothesis. You may have heard people say that a p-value is statistically significant. This means that, statistically speaking, we believe that the observed differences are due to something other than random variation. However, you should keep in mind that statistical significance is not the same as practical significance. Let's consider the following examples of statistical versus practical significance. You may have seen headlines several years ago that noted a connection between intelligence and fry preference, or that going to university increases your risk of brain cancer. The first one may be a fun fact, and certainly is not causal. Plenty of smart people don't like curly fries, although personally I think they're wrong, but the second one seems rather worrying. Should you drop out of university to save your brain? The finding that attending university is linked to a higher risk of brain cancer is based on a Swedish study. The researchers found a 19% relative increase in risk between participants with the lowest level of education, primary school, and the highest, university degree or higher, with a 95% confidence level. So far, this is all very concerning. But what the headlines missed is the size of the association. The sample was of 2 million men over 18 years. Roughly 1 out of every 600 participants developed brain cancer. As the baseline group, that would mean that out of 3,000 men with only a primary level of education, 5 would develop brain cancer. A 19% relative increase over 5 cases is 1 additional case. In other words, only 6 men with a university education are expected to develop brain cancer out of 3,000. The reason the study has statistical significance, but not much practical significance, is due to the very large sample size, so that even very small differences, such as 1 additional case of brain cancer, are magnified. Given enough data or enough tests, you can torture the data into saying anything. But much like torture in real life, just because the data tells you something doesn't mean it's true or valuable. For a detailed example of how multiple testing can lead to p-hacking, I suggest you read the XKCD cartoon on this slide. The URL is xkcd.com/882. The bottom line is, don't torture your data. It deserves better. So what did we learn in this lesson? Here are the key takeaway points from this lesson. 1. Hypotheses are predictions about the data. 2. Choose appropriate tests. Not every test will work for every type of data, and an inappropriate test will give you wrong or meaningless results. 3. Consider possible sources of errors and plan ahead to prevent or reduce them. 4. Finally, always remember that not rejecting the null hypothesis is not the same as saying the null hypothesis is true, and accepting the alternative hypothesis is not the same as saying the alternative hypothesis is true. We don't actually know, but we have made our best guess with the data and the tools that we have available. In the next lecture, I'll discuss detailed examples of one-sample hypotheses and two-sample hypotheses. Thank you. Welcome to part 2 of the lecture on fundamentals of hypothesis testing methodology. In part 2 of this lesson, we're going to work through some examples to test hypotheses with real data. This should help you better understand how to apply what you learned in the previous lesson. As I explained in the first lesson in this lecture, we can conduct both one- and two-sided, or tailed, tests with both one or two or more samples. Let's get started with hypothesis testing using the mean. Hypotheses with one sample involve comparing a statistic to some other value. In the case of a one-sided hypothesis, the sample statistic will either be above or below the other value. With two-sided hypotheses, the sample statistic is expected to equal some value. For both one- and two-sided hypotheses, when the statistic we want to test is a mean, we use either Gauss or t-tests. The Gauss, also known as the z-test, is used when the variance is known. We use the t-test when the variance is unknown or the sample size is small. With the Gauss or z-test, we calculate the z-statistic by subtracting the value or population mean from our sample mean, then dividing by the variation divided by the square root of the sample size. We then compare our z-statistic to the z-score for our selected significance level, or alpha. If our significance level is 5%, then alpha is 0.05. The z-score for this alpha level is either 1.65 or negative 1.65 if it is a one-sided test, and either 1.96 or negative 1.96 if it is a two-sided test. Let's practice this by asking if AIPD students are taller than 1.7 meters on average. Our null hypothesis is that students are not taller than 1.7 meters on average, meaning that they are shorter or equal to 1.7 meters. Our alternative hypothesis is that AIPD students are taller than 1.7 meters on average. We take a sample of 100 students and we calculate a sample mean of 1.78 meters with a variance of 0.25 meters, which is 25 centimeters. We can thus calculate a z-score of 3.2. Because 3.2 is greater than 1.65, we can reject our null hypothesis and conclude that AIPD students are in fact taller than 1.7 meters on average. But what if we wanted to know what our p-value is? How unlikely is it that our sample is from a population with a mean height of 1.7 meters? We can use a p-value calculator. We enter our test statistic of 3.2, that we are using a 0.05 significance level, and that we have a one-sided hypothesis. We get a p-value of less than 0.001, which is further proof that our results are statistically significant. We therefore reject the null hypothesis and accept our alternative hypothesis, and conclude that our sample is definitely not part of a population with an average height of 1.7 meters. Now let's try a t-test. There are several types of t-tests, but when we have a single sample, we use a one-sample t-test. The formula for the t-test is similar to the z-test, but not quite. Here, we calculate the t-statistic by subtracting the value, or mean, of the population from our sample mean, then dividing by the standard deviation divided by the square root of the sample size. We also use t-scores rather than z-scores. T-scores incorporate degrees of freedom to adjust for the smaller sample size. For this test, we'll ask the same question. Are AIPD students taller than 1.7 meters on average? Again, our null hypothesis is that students are not taller than 1.7 meters on average, meaning they are shorter than or equal to 1.7 meters. Our alternative hypothesis is that AIPD students are taller than 1.7 meters. Remember that t-tests are used when we don't know the variance or we have a small sample size. Here, let's say we have a second sample of only 25 students with a sample mean of 1.9 meters and a variance of 0.2 meters. We can thus calculate a t-score of 3.75. We need to calculate the appropriate threshold by consulting a t-value table. Because we have such a small sample size, we need to make adjustments based on our available degrees of freedom, which is equal to our sample size minus 1. The t-value for a 95% confidence interval and 24 degrees of freedom is 1.71. Because our t-score of 3.75 is greater than the threshold t-value, we can reject our null hypothesis that AIPD students are not taller than 1.7 meters. Why don't you try determining the p-value for this test on your own? As with one-sample problems, you can have one or two-sided hypotheses for two samples. For one-sided hypotheses and tests, our null hypothesis is that the samples have equal means, and our alternative hypothesis is that one mean is larger than the other. For two-sided tests, our null hypothesis is that the samples have equal means, and the alternative hypothesis is that they do not have equal means. The type of test we choose is again dependent on if the variance is known or not, but also if the samples are independent or dependent. We've already discussed how to use Gauss and t-tests for one-sample problems, and you can use both types of tests for two-sample problems if the samples are independent and you either know the variance or at least know that the variance is equal. For independent samples with unknown and unequal variance, you would use a Welsh test. For dependent samples, you would use a variation of the t-test called a paired t-test. We'll discuss how to use a Welsh test and a paired t-test in the next few slides. The formula for calculating the test statistic of a Welsh test may look complicated, but it's really just the means of each sample divided by the variance of each sample divided by their respective sample sizes. So let's compare the two samples we tested for the one sample problem examples. Are they both from the same population? For space, we'll write the measurements from our sample in centimeters rather than meters. The calculations remain the same. We calculate our test statistic as negative 2.544. Welsh tests use the same decision criteria as the one-sample t-test, except that the degrees of freedom are not the sample size, n minus 1, but rather v. We calculate degrees of freedom using the second formula on this slide and find that v equals approximately 44. This calculation is not shown. The t-test for a two-tailed test with 44 degrees of freedom is 2.015. Because the absolute value of our test statistic is greater than our t-score, we reject our null hypothesis that these samples are from the same population. Since these were both supposed to be samples of AIPD students, we'll need to go back and check our sampling procedures to make sure we didn't accidentally include a group of tourists. Let's try one last test. What if, instead of taking two samples of students, we ran an experiment to see how well students perform a task before and after their morning coffee? Specifically, we want to see if the student's performance improves after having some coffee. Our null hypothesis is that drinking coffee won't make a difference in our students, so the mean of the post-treatment measurement, x, will be less than or equal to the mean of the pre-treatment measurement, which is y. Our alternative hypothesis is that drinking coffee does in fact make a difference, and thus the post-treatment mean will be greater than the pre-treatment mean. The table on this slide shows the measurements for 10 students. For each student I, we calculate the difference between their pre-treatment score, yi, and their post-treatment score, xi. This difference is di. We then use the sum of all the differences to calculate our sample mean and use the sample mean subtracted from each individual difference to calculate the sample variance. I've already given the values for the sample mean and sample variance here, so let's just calculate our test statistic. The formula for calculating the test statistic of a paired t-test is the sample mean divided by the standard deviation multiplied by the square root of the sample size. For this sample, our test statistic is 3.35. We have 9 degrees of freedom, and with an alpha of 0.05, we find that our test statistic is greater than the value we would expect if drinking coffee made no difference in student performance. We can therefore reject the null hypothesis and accept the alternative hypothesis that drinking coffee in the morning makes students perform better. Now let's move on to hypothesis testing concerning proportions. Sometimes we may want to know if the proportion of a sample or group is equal to that of another sample or the population itself. In these cases, we would use a binomial test of the proportion or probability. In both cases, we use binomial tests, although the formulas differ slightly depending on our number of samples and if we are conducting an approximate or an exact test. The exact binomial tests require a statistical program such as R because it uses the binomial distribution. So we're only going to look at approximate binomial tests here. The approximate binomial test approximates the binomial distribution by the normal distribution and is appropriate if n is large and the proportion under consideration is neither too small nor too large, meaning that the condition n p times 1 minus p is greater than or equal to 9. So first we'll consider a one-sample problem. Let's say that last year, 30% of AIPD students took at least one statistics class. This year, the statistics department has advertised their class offerings heavily in order to encourage higher enrollment. Now, 35% of AIPD students are enrolled in a statistics class. Is the difference in enrollment percentages a real difference, or is it due to chance? Our null hypothesis is that the two proportions are statistically equal. Our alternative hypothesis is that this year's percentage of enrolled students is greater than last year's. For the sake of the example, we'll say that AIPD has 1,000 students. We calculate our test statistic as 3.45. Because 3.45 is greater than the z-score for an alpha of 0.05, we can reject our null hypothesis. It seems that AIPD student enrollment in statistics classes has increased this year. We have one last test to cover, which is the approximate binomial test with two samples. As with the one sample test, we approximate a binomial distribution, this time approximating the sums of our samples x and y with parameters p1 and p2. Here, x divided by n1 and y divided by n2 are approximately normally distributed, and their difference, d, is also normally distributed under our null hypothesis that p1 is equal to p2. We can therefore pool the two samples to estimate p hat. To calculate our t-statistic, we use d and p hat. As with the one sample test, the approximate test with two samples is appropriate if n is large and p is neither too small nor too large. For example, let's consider two competing lotteries. Both lotteries claim that every fourth ticket sold will win. Are the probabilities of winning each lottery actually the same? We can calculate our probability for lottery A as the probability of winning if you participate, which is 14 divided by 63. Our probability of winning lottery B is 13 divided by 45. Our difference is -1 divided by 15, and our combined probability is 1/4. We use these values to calculate our test statistic, and we find that our test statistic is -0.79. Because the absolute value of our test statistic is less than our z-score of 1.96, we fail to reject our null hypothesis, meaning that we have no evidence that the two lotteries have different winning probabilities. Having calculated the two-sample approximate binomial test, let's now wrap up this lesson. This lesson was very formula-heavy, but there are a wide variety of available tests for you to choose. However, this means that when you choose a test, there are a number of factors you need to consider. The better you match your test to your data, the more confidence you will have when you make a decision about whether to accept or reject your null hypothesis. In the next lecture, we'll look at ANOVA, which is an acronym for Analysis of Variance. Until then. Welcome to Part 3 of Fundamentals of Hypothesis Testing. This is the last part of this lecture. In this final lesson about hypothesis testing, we'll discuss the analysis of variance, also known as ANOVA. We'll discuss the assumptions that ANOVA requires, work through a one-way f-test, and then finally consider the Tukey-Kramer procedure for multiple comparisons. Let's get started. ANOVA is a shorter way of saying analysis of variance. It comes from the first two letters of analysis, the O in of, and the first two letters of variance. ANOVA is, in its simplest form, a test of whether multiple populations means are equal. Because it can evaluate multiple data points, it is often used for testing the goodness of fit of regression lines. Regression is covered in Lesson 9, so if you're not familiar with it yet, you may want to skip ahead to the lectures on regression and then come back to this one. ANOVA requires that three assumptions are met. First, that the errors, or residuals, between your expected and observed values are normally distributed. We can test for normal distribution of errors using several different tests, but the most common one is the Shapiro-Wilks test, which we'll consider in a moment. The second assumption is that the variance of the errors is equal. There are several ways to test for this normality, including the F-test, which we'll discuss for a different purpose later on. For now, we'll look at the Bartlett test. The final assumption is that the data are independent. There's no test for this. Rather, independence of data must be addressed during the design and data collection stages. The assumption of normality is important for when you have a small sample size or a small effect size. For larger sample sizes, the assumption of normality can be relaxed. Additionally, with large sample sizes, it may be more difficult to conduct a normality test, so you may want to simply graph your data as a histogram. In the Shapiro-Wilks test, AI is derived from several vectors, but is essentially the constants of randomly distributed variables. Xi, with I in parentheses, is an order statistic. The null hypothesis is that the distribution of errors, or residuals, is normal. Small values of W are indicative that the sample is not normal. If we accept the null hypothesis, then we can assume normality of our error distribution. I would suggest using your favorite statistical program to conduct the Shapiro-Wilks and other tests we will discuss today. Bartlett's test tests to see if multiple samples have equal variances, which is also known as homoscedasticity. This is a difficult word to say sometimes. Our null hypothesis is that the variance of our samples is equal, while our alternative hypothesis is that they are unequal. If the p-value is not significant, then we can conclude we have equal variances. However, Bartlett's test can be sensitive to non-normality, meaning that if the distribution of the samples is not normal, Bartlett's test may test for non-normality instead of homoscedasticity. Levine's test can be less sensitive to non-normality, but it may be best to test the normality of your samples first. Now let's look at one-way ANOVA F-tests. As I mentioned before, the F-test can be used to test for normality. A one-way or ANOVA F-test is used to check if the expected values of a variable within predefined groups differ. Because we are testing to see if there is any variance between groups, this can be a way of testing several groups at one time, rather than needing to conduct pairwise tests. I won't go into all the details about calculating an ANOVA F-test because you can use a statistical program such as R to do that for you. However, you should remember two things. The first is that it only tests for differences between all groups, so we can't tell which group is different from the others, only that there is a difference. The second is that when you are testing only two groups, the F statistic is equal to the student's t-test statistic squared. When you conduct an ANOVA test in R, you get an ANOVA table, which reports the degrees of freedom, sum of squares, mean squares, and F and P values. Exactly what all of these values mean is something that will be covered more thoroughly in the regression lecture, but the F and the P values are what we're interested in when we're conducting an F test. Let's try this with an example. Let's say we want to test two different types of plant growth treatments, like a fertilizer, compared to a control group to see which one increases a plant's size the best. This is from the R dataset Plant Growth. You can find more information about the dataset and the code for this analysis at the link on the slide. There are 30 observations in the dataset, so we'll just look at a random sample here. We can also see the mean and standard deviation of each group. It looks like the treatments may have resulted in different plant weights across the groups, but we won't know for sure until we conduct a test. Our null hypothesis is that the mean of each group is the same. Our alternative hypothesis is that at least one mean is not the same. Remember though, we won't be able to tell which mean is different, just that at least one of them is different. We'll assume that all ANOVA assumptions are met. Because R calculates a p-value for us, we don't have to compare the F statistic to anything here. Instead, we can see that our p-value is less than our alpha level, meaning we should reject our null hypothesis that all the group means are the same. However, we still don't know which means are statistically different, and we shouldn't just guess. We'll need to follow the Tukey-Kramer procedure to test the means against each other. The Tukey-Kramer procedure, often just called the Tukey procedure, spares us the necessity of having to conduct individual pairwise comparisons of our three different groups. This would be A against B, A against C, and then B against C. It relies on the same assumptions as ANOVA. The Tukey test is essentially a t-test where YA is the larger of the two means being compared, YB is the smaller of the two means, and SE is the standard error of the sum of the means. As with the ANOVA test, the null hypothesis is that the means are the same, and the alternative hypothesis is that one of the means is not the same. However, when we conduct a Tukey test, we will see which of the means are different from the others. As you can see, the R results compare each of the three groups to each other and provide the difference between the means, the lower and upper bounds of the confidence interval, and the p-values after adjustments for multiple comparisons. The p-values for the comparison of treatment 1, A, versus the control, C, and for treatment 2, B, versus the control, C, show that neither treatment is significantly different from the control. However, the comparison of treatment 2 versus treatment 1 shows that there is a statistical difference between the two treatments. So how should we interpret this? We could say that the control is no better or worse than either treatment, But if we only have the choice of treatment 1 or 2, we should choose treatment 2. However, if applying a treatment has an external cost, it might just make sense to continue working with the control. So we've now reached the end of the 3-part lecture on hypothesis testing. So let's review the overall key points. Remember, hypotheses are predictions about the data. You always need a null hypothesis and at least one alternative hypothesis. When you're choosing a hypothesis test, consider your data. What type of value are you testing for, and are the data normally distributed? How many samples do you have? Are the samples independent or dependent? Is your variance known or equal? Make sure to check any assumptions you've made about the data, since this will help reduce errors in your analysis. And lastly, always keep in mind that not rejecting the null hypothesis is not the same as saying it's true, and accepting the alternative hypothesis is not the same as saying that that is true. Good luck!